In topic 5, you're going to need to know your exponent rules. Now, you've seen these before, but they're often forgotten, so let's review a little bit. Many of us know that x times x makes x squared. But then when it comes to something like x times x squared, we may not remember what to do. Well, we always want to assume that there's actually a power here of 1 if we don't see one. And this one would actually become x to the third. Now, if we did this enough, you'd see the pattern that, for example 1 here, x to the 5th times x to the 7th is actually x to the 12th. That's because x to the 5th is really 5 of these x's written out multiplied by each other, and x to the 7 is 7 of them. Your total number of x's is actually 12 of them. That's why we actually changed the power. So here we would say we'd have m to the 11th. With numbers, though, that doesn't mean we change our multiplying. If someone told you to take 2 times 5, you'd still get 10. But we'd have x to the 10th as well because 6 plus 4 is 10. And it can work with negatives. Here we'd have p to the 6th. You'd be adding that negative 2. So the multiplication rule when dealing with exponents, if you have like bases, these numbers on the bottom or variables on the bottom are the same, when you're multiplying, you can add your exponents together. So that would be our general multiplication rule. Now, if you're dividing, so this would actually look like x times x times x times x over x times x times x. That's the longer version of it, if you will. Well, if I ever asked you, what is 8 divided by 8? You just say it's 1. Like they cancel, they reduce. So I could reduce each of these x's that are stacked on top of each other, and I'm just left with the x. Now, remember, with the numbers, we still take 20 divided by 5 here, and I'm going to get 4. But if I wanted to write this all out, now I don't really, but for time's sake, I think I have a little time here. There's my 9m's, and I'd have 4 down here. I would be canceling out 4 of them, or reducing 4 of them. I would have 1, 2, 3, 4, 5 left. What could we do with 9 and 4 that would give me these 5 left? Well, we would subtract them. I'd think of them as reducing each other. So this one, I'd have 7 on top and 10 on bottom. That means I'd have 3 left over. Now, one thing we want to think about, it's important to put your leftovers, or the ones that were not reduced. See how we only had 1 left over on example 1? It was in the top, so I left it on the top. Or this m to the 5th, he was up top. This one had 3 x's in the denominator left over. It is also legal, though, to write it as x to the negative 3, because if we think about 7 take away 10, we get negative 3. We'll discuss this property a little later when we talk about negative exponents. On this one, we know 3 and 9 reduce to 1/3. X to the 5th and x squared, I'd have 5 of them on top and 2 on bottom. So 3 would be left over on top. And 9 of the y's written out here, and 15 down here, so I would have 6 left on the bottom. So our subtraction will be applicable when our bases are the same and we're dividing. That is, if my bases are both a here, and the powers are m and n, I will subtract n from m. When it comes to that negative exponent, so when we saw that 1 over x to the 3rd, I also mentioned it could be written like this, x to the negative 3rd. But nobody likes a crabby exponent, kind of like a crabby toddler. If they're not behaving, you might say, you know what, you need to go down and take a time out. Go into a different location. We do not want to end up with negative exponents. We always want to change them. So, hey, there's that example again. This could be x to the negative 3rd, because 7 take away 10 is negative 3, but we want to put it, now right now it's over 1. But if I want it to be a positive x to the 3rd, I can put it in the opposite spot of the fraction. That would be back in the denominator, since the numerator has where the negative is happening. So our rule would be, if you ever have a base, like x, to a negative power, put it in the denominator and it'll be a positive power. Or if you ever have a positive power and you want to change it to be a negative, you'd put it in the basement as well. Something that could happen also is if you had started with something like this. I know normally we read left to right, but if you ever have a negative exponent in your denominator to start, move it up top. So again, we would write that back as x to the m in the numerator. All right. We'll also be getting into rational exponents. Rational is fraction. We're going to work with fractional exponents. So the same rules that we just discussed apply, but now we need to be able to add fractions. Instead of just adding, we're going to talk about what this means here in this next chapter. So a little foreshadowing, if you will. If we put some numbers in, it might make it a little bit easier. So we could try putting an actual number in here and plug it into our calculator and see what patterns we find. But just as a little extra hint here, we're going to find that the 3 is what the power is, and the 5 is what the root is. Whenever you see a rational exponent, a fraction in your exponent, the power is the top number, and the root is the denominator's number. So our rule says this. If you have an a over b as your exponent, the a is the power, and the b is the root. I like to say you have the power over the root, because you can do this. Now, a few practice problems. You could try some of these here. These ones have to do with taking a base, say here like x, to a power and then to another power. Well, this would actually look like x squared times x squared times x squared. And if I wrote it out really longhand, x squared is x times x. This is going to be x to the 6th. Now, I don't really feel like writing that out each time. So what could I have done with 2 and 3 just to get this 6? We would have multiplied them. And that's going to be our next rule. I'll come back here in a second. But when you ever have a power to another power, so here's my base, a, that's my base. And this is my power that a is being taken to. But it's all being taken to another power. We'll multiply those powers. So if I come back and try another one. Now it's important when you see the 7, you want to take every base in here, the 7 and the x, to the squared. 7 squared is still 49. We do that like normal, 7 times 7. X to the negative 5th to the 2, when you power to a power, you multiply. So you'd have negative 10. Here I'd have 2 to the 6th, which would be 32, or no, 30. Sorry, that's going to be 64. That one actually came out to a number because it didn't have a variable with it. And then, again, you can just take your 5 to the 3rd like normal. So we'd have our 125. X to the 6th to the 3rd. It's another power to a power. It gets bigger much quicker than just the adding. So I'd have x to the 18, y to the 21st. And finally, because this is negative, remember, nobody likes a crabby exponent. We could rewrite it as this all to the positive 2. Notice how I took everything in those parentheses down to the denominator. So I'd have 1 over 2 squared is still 4, and power to a power would mean we multiply. One other thing I just want to mention, anything to the 0 power is 1. X to the 0 power is 1, 5 to the 0 power is 1, 126 to the 0 power is 1. You can try even these ones on a calculator. We want to keep in mind that 0 power, that anything to the 0 power will always be 1.